We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
The main thing that Chandra does is take these superb, sharp images.
Nothing as beautiful as Chandra sailing off on its way to work.
NASA's Chandra X-ray Observatory, in orbit since 1999, studies the high-energy universe, where black holes, exploded stars, and mysterious matter hold sway. X-ray telescopes like Chandra are not like telescopes you find in backyards or at the local observatory. In addition to being above the Earth's atmosphere, they need to have special mirrors to detect the X-rays that pass through most objects. Let's listen to scientist Martin Elvis explain more about Chandra's technology.
The main thing Chandra does is take these superb, sharp images. How does it do that? Well, X-ray telescopes are different from optical telescopes. They have a very different shape. Although in fact, they're really reflecting light in just the same way as optical light. It's just that with X-rays, you have to coax them into being reflected. If you have a normal mirror, you look at yourself in the mirror and the light's going in and straight back, so it's being bounced through 180 degrees. If you try that with X-rays, they just get absorbed. But you can get specular reflection if you come into a grazing angle of a degree or less. Once you get that specular reflection, X-rays act just like optical light. You can concentrate them and focus them, no problem. Trouble is, you're only bending the light through 1 degree on each reflection. We end up having 2 reflections in our mirrors. That means that the light's only coming together very, very slowly, so we tend to have very long telescopes, most of it being just empty space. We're just waiting for the light to converge down to its focus. The bad thing about these mirrors is you're looking almost edge or end on at a cylinder, so the area of glass that the light's reflecting off is only a thin annulus. So what we do is pile a whole bunch of telescopes nested one inside the other to build up the area. But basically you still have to polish 100 times as much glass as you would for a normal optical telescope. So this 1.2 meter diameter Chandra mirror is focusing light down onto an exquisite point just 1,000th of an inch across. That's why Chandra's powerful.
In addition to its special mirrors, Chandra also travels in an unusual orbit around the Earth. Unlike its partner mission, the Hubble Space Telescope, Chandra cannot be serviced by astronauts. That's because it does not circle relatively closely to Earth as Hubble does. Martin explains more about why Chandra travels in unusual circles, or, more accurately, ellipses.
Chandra doesn't just go above the atmosphere, it goes 1/3 of the way to the moon, getting well away from the Earth. But it can't get above the atmosphere twice, so why do we bother? The answer is to be much more efficient at observing. It's only a small telescope and we tend to have to observe a long time. But if we're down where the space station is, or the shuttle can get to, then wherever you want to look, half the time the Earth is in the way. Not what you want if you're looking with an X-ray telescope. So instead, if you can afford the energy to push you way out there, the Earth looks very small, and you can point almost anywhere without it getting in the way. That's very useful for many observations, but mainly it doubles the efficiency of Chandra.
Now that we've heard a little about how Chandra works, let's listen to Martin give us an introduction to how X-rays are produced in the universe.
There are 3 different ways you can get matter to be that hot. One is simply an explosion, like a supernova, such as the one in 1987 in the Large Magellanic Cloud. What we see there is very fast-moving gas that's hit material on the outside and is now glowing with a shock at a few million degrees. The next way you can make X-rays is a more complicated process, and that's by having very fast-moving charged particles in a magnetic field. Basic law of physics is that any charged particle moving in a magnetic field gets swirled around, and in doing so it's accelerating around a bend, and accelerating charge radiates. It turns out there are lots of places in the universe where we get magnetic fields and very fast-moving, we call them relativistic particles. They're moving very close to the speed of light. The Crab Nebula, for instance, is powered by a pulsar at the center, which has so much energy in it that the little wisps and things you see in the image, which look like they're sort of swirling around the nebula, they aren't swirling at all, they're moving outwards at extraordinary velocities. This type of X-ray making mechanism we find very commonly also in quasars and blazars, which are things with these huge jets that come out, maybe many times the size of a whole galaxy, and these are powered in X-rays by the same mechanism. The third way of making X-rays is perhaps the least likely. It's just dropping something down a hole. If you have a lot of mass somewhere, like a planet, or better still a neutron star or a black hole, and you drop something in, then it speeds up, and when it hits the surface or some other gas coming from a different direction, it heats up. A spaceship re-entering the Earth's atmosphere does the same thing. It starts glowing very hot. spacecraft is generating heat through friction with the air and slowing down. And that's just transferring the energy of its motion into heat. So it's a very simple process, really. It just turns out that most of the X-ray sources in the sky are powered this way.
For more information about the Chandra X-ray Observatory, visit our website at chandra.harvard.edu.
This was a production of the Chandra X-ray Center, Cambridge, Massachusetts. NASA's Marshall Space Flight Center manages the Chandra program. The Smithsonian Astrophysical Observatory controls science and flight operations from the Chandra X-ray Center.